Okay, here we have Gibbs free energy. Gibbs free energy is a very important thermodynamic term that has a lot of application in real life. It was defined by Willard Gibbs back in the 19th century. So just a little introduction here. Gibbs free energy is a thermodynamic potential that measures the usefulness of process initiating work obtainable from a thermodynamic system at a constant temperature and pressure. So to make that sound a little bit easier here, we're going to define free energy. In other words, available energy. So available energy is the energy that we can use to do work. So it's energy out there that we can obtain, and we could use that to do work in our human bodies. So that delta G, which is change in um, available energy or change in free energy, is defined by this equation here. So delta G is equal to the change in enthalpy minus temperature times the change in entropy. So in order to explain this equation here a little bit easier, we use spontaneous reaction. So what is a spontaneous reaction? A spontaneous reaction is a reaction that once you give it a little push, it will go on its own. So in order to explain that further, we have three examples below. First of all, we have a ball. A ball is at the very top of a slope, and so we're gonna look at the overall energy of the system in terms of enthalpy, but then in this case it will be potential energy. So potential energy here is equivalent to the enthalpy and is the total energy of the system. So at the very top, the total energy of the system is is very high, right? And if you give the ball a little push and then let it roll down, it will come down here, and you will end up with H2, which is the final enthalpy. So if you look at H2 and H1, H1 is way bigger than H2 because at the very bottom, the potential energy is way smaller. So the overall energy of the system has gone through a decrease. Our second example here is diffusion. So in a container where you have a whole bunch of molecules that are compressed, they're congested, and they're just waiting for you to give them a bigger volume to open up the space. And what they will do is they will chaotically move and try to spread themselves out through the whole entire volume. And this is a notion called diffusion. So here in this case, we have an initial situation of molecules that are congested at the very end here, and then we gave them a bigger volume, and then meaning in other words, their disorderliness or entropy increased from this point to this point. So here we have S1, which is the initial entropy, um, less than S2. So that's the second scenario. The third one we have here is a little bit different. We have a cherry bomb, and here's the cherry bomb, right? Um, we want to induce some spontaneity in this, but how would we do that? Okay, so we're gonna add a little bit of heat to it. We're gonna increase the temperature, and so we have an initial temperature of room temperature, and then the second temperature we have increased it a little bit. And so just like I said, a spontaneous reaction, you have to give it a little push. And so if you give it a little push, it'll go on its own. So what happens when you increase the temperature? Boom! It explodes. And so the change in temperature or increase in temperature caused for it to caused for it to explode. And so this is our third scenario. So in order to summarize this using our equation, so in the first case scenario, we had a decrease in enthalpy. Remember the ball the rolled down the slope. So we had a decrease in enthalpy. So what happened? So if you look at this mathematical equation, what happens if you decrease delta H? All right, delta G decreases. The change in free energy decreases. And in the second scenario, in diffusion, we increase delta S. What happens if you do that? It still decreases our delta G. So if in the third case scenario we increase the temperature, we induce some temperature to it. What happens if you have a high temperature on it? It decreases delta G. So the moral of the story here is that in spontaneous reactions, delta G is less than 0, and in other words, it's called exergonic reaction, and it's the reaction where energy is actually released. How about the other way around? If we have delta G equals 0, this is called non-spontaneous reaction, and in other words, it's called endergonic reaction. This is where heat or energy is actually absorbed. However, if we're neutral, there's no change in the free energy, then we have an equilibrium situation here. All right. So let us apply these notions in real life. We have photosynthesis here. So photosynthesis is basically the most basic form of photosynthesis is that carbon dioxide reacts with water using light energy from the sun and chlorophyll from the plants to create carbon dioxide or glucose and oxygen. So if you look at the very bottom equation here, we have 6 molecules of carbon dioxide and 6 molecules of water, and you induce light energy to it. It gives you 1 molecule of glucose and 6 molecules of oxygen. So in total, on the left hand side, we have 12 molecules. And on the right hand side, we have 7 molecules total. So if you look at our second demonstration, we had diffusion. Entropy here on the left hand side is bigger than entropy on the right hand side because we have more molecules here, and so there's a decrease in entropy, and so there's an increase in energy because light energy is absorbed from the sun. So both cases, meaning enthalpy is increased and entropy is decreased, is kind of like the reverse of what we had explained. So in this case, this will actually increase delta G. So photosynthesis in general increases the change in free energy. And this is where we get the energy of our food. And God, we had a really, really, really nice Thanksgiving. We had a lot of good food here. So basically, once the plants do the work, we have mashed potato here from plants. We have our stuffing here. We have puddings. We have potato. Man, this was really good. So this is the point where we consume the energy, and once we consume energy, we have to go through the cycle of releasing the energy too, and that's the reverse of photosynthesis basically, and that is defined by a notion called cellular respiration, and it's just showing a reverse. Its equation is just basically the reverse of photosynthesis. So we have glucose here on the left hand side and 6 oxygens, and that reacts to give you to release carbon dioxide, water, and energy in the form of ATP. So the energy that was stored, the energy that was absorbed by the plants in photosynthesis, is here released again in ATP form. And so when this guy here, we have a little video here of a guy who who had a really, really good Thanksgiving. and he basically wanted to work it out too. So he went on a treadmill and then started running. So right now, as he's doing so, this equation is basically happening. He is using the glucose that he ate, and then he's breathing in oxygen, and then when that reaction goes, it creates carbon dioxide, which he breathes out, and water, which he sweats out, and of course the energy that he's using to run. So basically, Gibbs free energy applies to him as well. So the moral of the whole notion here is that there's thermodynamics. In other words, Gibbs free energy has a lot of applications, and one of the major applications are um, the mechanism of our food intake in calorie burning. So that was my small summary of Gibbs free energy. I hope it was helpful.